Hello everyone, and welcome once again to another interesting physics class. Today we're going to talk about the refraction of light through a triangular prism, as we have right here before us. And this is one of the most interesting physics topics I have ever come across. And today I'm going to share with you a few things about this concept, and I will also show you how to derive the formula for the angle of deviation under normal deviation conditions. And I'll also show you how to derive the formula for the angle of deviation under minimum deviation conditions. Without further ado, let's get down to business. Suppose outside of this prism is air. Let's say outside is air, and this is the prism. Okay, outside is also air. This means that the light wave is going to travel from air, which is an optically rarer medium. When I say optically rarer, I'm talking about less dense. So air is a less dense medium, and light travels faster in air, okay, around this very area than in glass. Now, when a light ray hits the prism at an angle, okay, which we call I, this is actually the angle of incidence, and you can see it right here. It makes an angle with the normal. This is the normal line, okay, which is perpendicular to the face of the prism. Let's call this face here face A. We call this one down here our B, and here we say it's a C. So this prism has face AB and face AC. All right, now when the light ray comes from air and hits the prism at an angle, we call this the angle of incidence. As it hits this prism at surface AB, what happens? It's going to bend towards the normal. As it enters the prism, it bends towards the normal and hits the second surface, which we've called AC. When it hits, it's going to refract away from the normal, right? So this is basically the path of the light in the prism. It hits the prism at surface AB from air, which we call the angle of incidence, and it is always away from the normal. But when it hits the prism, it's going to bend towards the normal. You've seen it has bent towards the normal, and it makes an angle right here, which we're going to call R. This is our first refraction, okay? As it hits, it's going to refract, and we call this our first refraction. Remember that refraction occurs when light bends towards normal, or as it passes from an optically rarer medium to a denser medium. In this case, air is rarer, while the prism is denser. Now, as it travels inside the prism, as you've seen right here, it's going to hit the next surface. And as it hits this surface, it's also going to make an angle. So this is the angle of incidence, the second angle of incidence, but we can call it R prime. Okay, so this is the second angle of incidence. And as it hits the surface, what happens? It's going to bend away from the normal again, because it's not going from an optically denser medium to, in this case, a rarer medium. Okay, it's going from glass, and it's actually moving towards air or into air. Now it makes another angle here, and this whole angle here is called the angle of emergence, which I'm going to call I prime. So this is the angle of emergence. It is the angle with which the light wave or the light ray emerges or leaves the prism. Okay, now this angle up here is called the apex angle or the angle of prism. Okay, it's called A. We can also call it the angle of prism. And there is also another angle here, which we're going to call theta. All right. So these are basically the angles in a prism. Now, let's talk about the deviation right now. Suppose this light ray didn't go straight. Okay, let's say it didn't deviate, or let's say it did not bend towards the normal, as you've seen in this very case. Let's assume it went straight up here based on its original path. Okay, this would have been the path of the light. But because of the material of the prism, it went from an optically rarer to a denser medium. It bent towards the normal. Now, this you can see right here, it has made an angle, okay? An angle. So this angle is between the original path and the deviated path, okay? As you've seen right here. So we call this one here our first deviation, which is deviation 1. All right, this now becomes our first deviation. And as you've seen right here, suppose this light ray, as it has gone outside, we can also extend this line. Okay, we can extend this line here. And you've seen there is also another deviation here. Okay, so this angle is between the refracted ray and the deviation. Okay, so we now call this our deviation 2. You've seen? So there are actually basically two deviations. The first one occurs immediately, it refracts inside the prism, and the second one occurs as it is about to leave the prism. All right, so this angle right here is the total deviation. I'm going to explain this to you as we journey through the lesson. All right, so these are basically the angles in a prism, and I'm going to help you understand it. So to derive the formula for deviation, or the angle of deviation under normal conditions, under normal deviation conditions, what do we do? Let's analyze all the angles step by step to see what we're going to get. All right, so the first one right here that I'm going to carve out is this very shape. So this is the shape. Okay, let me use black so that we can understand better. Here, this very shape is seen as something like this. And here we have this. Okay, so this one is our deviation 1. And here we have our deviation 2. And up here we have our total deviation, which we've called delta. And based on the exterior angle theorem, which says that the sum of two opposite angles, okay, or the sum of two opposite angles or interior opposite angles is equal to the exterior angle. You've seen that delta 1 and delta 2 are two interior angles and they are opposite to each other. Okay, therefore we now say that the total deviation delta is equal to delta 1 plus delta 2. We call this our equation 1. As we've seen right here, the total deviation based on the exterior angle theorem that says that the sum of two opposite interior angles is equal to the exterior angle. This is the shape of the shape actually carved out, which we're going to call, let's say, our P. Okay, so this very P here, I carved it out here, and we've seen that based on the exterior angle theorem, these two angles that are opposite and inside here are actually equal to the exterior. So we call this our equation 1. This means that the total deviation is given by the first deviation plus the second deviation. We keep this aside. Now let's also go ahead and analyze another important shape right here. So you've seen that this one is inclined at 90 degrees, okay, to face A, B. And this shape also, this line here is also inclined at 90 degrees, okay, at face AC. Therefore, we can carve this out, okay. So I'm going to carve out the apex angle, carve out this point, the theta, and this point. Let's see what we're going to have. So we have this, we have this, we have this, and then we have this. Okay, I'm not too artistic. Let me try to erase it and actually draw a better diagram. All right, please pardon me on that. So right here, let me draw this. We have 1, we have 2, we have 3, we have 4. Okay, so right now, I would say, suppose this one is a 90 degrees as we have here. And here we also have 90 degrees. Okay, then up here we have our A, which is our apex angle. And right here we have theta. I'm sorry, this is not a perfect diagrammatic representation of the angles right here, but I hope you understand what I'm talking about. So we've seen that this is actually like a quadrilateral, and we know that the sum of all the angles in a quadrilateral is equal to 360. So we can now say we have our A, okay, plus 90, okay, as we have here, plus 90. And the next one is plus theta. This is equal to 360. Okay, so these are the sum of all the angles in a quadrilateral. Let's go ahead and simplify this. Here we have our A. 90 plus 90 will give us a 180. And we have plus theta is equal to 360. All right. Now, what do we do with this thing right here? We can now move the 180 across. We now have A plus theta is equal to 360 minus 180. Let's solve this further. We now have that A plus theta is equal to 180 degrees. So we call this our equation 2. This is a major equation, and it is really very important whenever we want to find our theta. Now, why is theta very important? It is necessary to find theta because you cannot find the angle of emergence under normal deviation conditions if you do not know this theta. Why? Because the angle of refraction under normal deviation conditions is not equal to the second angle of incidence, right? So you cannot just say, okay, let's use Snell's law to find this one. No, or let's use Snell's law since these are like they are actually in the same place. They're equal. No, they're not. You need to find this theta. This theta helps you to find your second angle of incidence, and at that point, you can now apply Snell's law to find this angle here of emergence. So we call this our equation 2. I'm going to write this one up here. So the first one we had was the total deviation is equal to deviation 1 plus deviation 2. This is our equation 1. Now the next one, we have that A plus theta is equal to 180 degrees. So this is our second equation. I'm going to erase all this here so that we can have enough space and continue with this interesting lesson. Remember that these equations are very important. You need to know how to analyze them so that you make no mistakes whenever it comes to calculating whatever you're asked to calculate relating to refraction of light through a triangular prism. The next shape we're going to analyze here is this triangle here. So if you look at this here, we have a triangle. So we can now say, I'm going to carve it out. This is the first one, this is the second one, and then we have this here. Okay, so this angle here is theta, as we have right here. The next one is r. This one is r prime. Since this is a triangle, we can now say that we know that the sum of all the angles in a triangle is equal to 180, right? This is a triangle, and r plus r prime plus theta must be equal to 180. Now let's see what we can get from that. We say that r plus r prime plus theta is equal to 180. Why is it equal to 180? Because this is a triangle, as we've seen right here. Now let's clean this up. We now say, okay, as we have right here, we have that r plus r prime plus theta is equal to 180. And we also know that equation 2 is also equal to 180. Since they are equal, we can now equate them together. Have you seen? If r plus r prime plus theta is equal to 180, and a plus theta is also equal to 180. Therefore, we can equate them together. Okay, so let me quickly do that. I'm going to clean the shape right here and then equate the two together. Now, I would say here we have r plus r prime, okay, plus theta is equal to this one here. We have our a plus theta, okay. So what do we do right now? We are basically going to move this across, okay. I'm going to move the theta across, and since it's a positive here, once it moves across the other side, it becomes a negative. Hence, we now have r plus r prime plus theta minus theta is equal to A. Okay? Now, you've seen this one is a minus. Here we have a plus. They can cancel out because theta minus theta will give you a 0. Now, you now have that R plus R prime is equal to A. Okay? So, let me explain this in a better way so that you can understand what is happening here. So, what this basically means is that our A, okay, which is in this case the angle of prism as we have up here. So the A represents the angle of prism is equal to R plus R prime. This means that if you want to find the angle of prism, which is in this case A, and you know your R, which is the angle of refraction at the first surface and the angle of incidence at the second surface, you can, if you add the two of them together, they're equal to this angle up here. So this angle and this angle added together are equal to the apex angle or the angle of prism. This now is now going to be our third equation. So let me clean up here so that we can write it and include it here. I'm going to clean it up here. Now we have that our A is equal to R plus R prime. This is our equation 3 as we've derived right now from these shapes. What next shape do we need to analyze right now? We have to keep on investigating them because a proper knowledge of all these shapes will help us to solve any kind of problem relating to this refraction of light through a triangular prism. The next shape to analyze here is this one out here. Okay, now we need to understand that vertically opposite angles are equal. If you look at this here, we have this very shape. So we have something like this. Okay, so this one right here can be seen as our angle of emergence, which is our I prime. And here we have our delta 1. Okay, sorry, our delta 2 or our delta 1. This is actually our delta 2. And then we have our R prime, right? Here we have I prime, as I've written here. We have delta 2, which is second deviation. And we have R prime, which is the angle of incidence at the second surface. We said that opposite, vertically opposite angles are equal. This means that these two angles here, delta 2 and R prime, are equal to I prime, which is in this case the angle of emergence. So the second deviation and the angle of incidence at the second surface, they are both equal to the angle of emergence. So from there we can now say that I prime is equal to deviation 2 plus R prime. All right, now let's get for the other one. We've actually investigated this very shape. Let's investigate this one as well. You've seen that they are also vertically opposite angles. And if we investigate this like this, let's say we draw this and we try to investigate. This is not so perfect, but I hope you understand what I'm trying to do right here. This is our angle of incidence. This is it out here. And right here we have a line, which you have right here. So the first one, the first angle is our first deviation, and the second one is our first refraction. Okay, this is our angle of refraction based on the fact that vertically opposite angles are equal. What do we do with this? We can now say, okay, let's bring it up here. We now say that I, okay, is equal to, remember this is our I prime, while this is our I, we can now say that I is equal to deviation 1, okay, plus refraction, the first refraction, okay? So this angle of incidence is equal to the first deviation plus the first refraction right here. Now, what do we do with this very information? I'm trying to derive the formula for finding the minimum the angle of deviation under normal deviation conditions. That's what I'm trying to do right now. And after that, we can now talk about the next one, which is under minimum deviation condition. Okay, now I'm going to make this deviation 2 and deviation 1 the subject of the formula in this case by moving the r prime across. Okay, I move the r across as well. And if we do that, for the first one, we're going to have that our I prime minus r prime is equal to delta 2. Okay, I got this expression from here where I made delta 2, or the second angle of deviation, the subject of the formula. And from this second one here, we also move the r across. And what shall we obtain? We have that I, which is the angle of incidence, minus r, which is the angle of refraction, is equal to the first deviation. What do we now do with this information? Let's go ahead and let's go ahead and combine them together to see what we shall get. Adding the two of them together is going to give us a very important formula which we need right now. Therefore, we say deviation 1 plus deviation 2 is equal to, for deviation 1, this is equal to I minus r, I put them in brackets, plus the deviation 2 is I prime minus r prime. Okay, now let's remove the brackets. But you need to remember that before we remove the brackets, that deviation 1 plus deviation 2 is equal to the total deviation here. You've seen the expression. Therefore, we're now going to replace this deviation 1 plus 2 with the total deviation. This now gives us the total deviation is equal to, I'm going to remove the bracket, we have I minus r plus I prime minus r prime. All right, now let's go ahead and pick the i's together. We now have that the total deviation is equal to, I'm going to collect the i's first. We have I plus I prime, and I'll pick the r's first. We have minus r minus r prime. Let's continue. We have the total deviation is equal to I plus I prime. Since we've seen that negatives are common here, okay, negatives are common, we can now factor out the negative. We put it outside and we open the bracket. Now, if you factor out the negative, what remains is r plus r prime. Now, you might be wondering, where did the plus come from? Well, once you factor out the negative, if you want to get the original expression back, just multiply. If you see here, we have a negative outside. Now, if you distribute this negative across the r and the r prime, what do you get? Negative times r will give you negative r, while negative times r prime will give you negative r prime. Therefore, we're also going to get our original expression back. So, but you need to remember that from here, we said that r plus r prime is equal to a. Okay, the first refraction plus the second angle of incidence is equal to the apex angle. Therefore, whenever we see r plus r prime, we simply replace it with a. Therefore, this now becomes the total deviation is equal to I plus I prime minus, we replace everything here with an a. Okay, everything will now be replaced with an a, and this is the major equation with which we calculate the angle of deviation under normal deviation conditions. This is the equation here. In case you're given, okay, let me write it up here. We have that our total deviation is equal to the angle of incidence plus the angle of emergence minus the angle of prism. This is a major equation. Okay, this is a major equation. I need you to understand that this I prime here is the angle of emergence. So to find your deviation, your total deviation, Under normal deviation conditions, what do you need? You need um, the angle of prism, which is in this case A, okay? You need your angle of incidence, and you also need your angle of emergence. Without your angle of emergence, you can never find a deviation. And without your angle of incidence, you can also never find the deviation. So this is how to derive the equation for calculating the angle of deviation under normal deviation conditions. What about the angle of deviation under minimum deviation conditions? How do we derive that? Well, everything shall be gotten from this. Okay, we shall get everything from this, and I'm also going to show you how it actually works. Now, how does it really work in this very case? Well, we're simply, let me clean this very part so that we can go to the next one, which is actually talking about the minimum deviation conditions. All right, so we now say under minimum deviation conditions, I'm going to make this distinction. We say under minimum deviation, so this DEV means deviation conditions. What happens under minimum deviation conditions? So we're going to pick this formula here, and we say this, okay, is equal to I plus I prime minus A. So this is what we're going to use to derive the formula for calculating the minimum angle of deviation under minimum deviation conditions. But now we're going to move this negative A across. Okay, move the negative A across. When we move it across, we now have our total deviation, okay, plus A, it's a minus, and once it moves over, it becomes a plus, is equal to I plus I prime. All right. Now, what do we do with this very information? Now, we're going to now make a distinction right now. Let's make a distinction here by saying at this point, it's not going to be deviation minimum, okay? Deviation minimum, okay? Which means under minimum deviations. We now have to understand that whenever we are experiencing minimum deviation on it in a triangular prism, rather, the angle of incidence is equal to the angle of emergence. Under minimum deviation conditions, the angle of incidence is equal to the angle of emergence, but under normal deviation conditions, the angle of incidence is not equal to the angle of emergence, okay, which is in this case, I is not equal to I prime under minimum deviation conditions. I mean, under normal deviation conditions, but under minimum, they are both equal. So what we're going to do right now is that I'm going to replace this I prime with an I. Since they are the same, we do a replacement. Let me do that here. This is our prism, if I forget. Okay, so we now say, remember we're talking about under minimum deviation conditions. Remember that under minimum I, okay, which is the angle of incidence, is equal to the angle of emergence. Okay, so if they're equal, we can now say that I is equal to I prime, as I've written here. Then here right now, we're going to replace this I prime with I, because since they're equal, we can actually replace them. Therefore, we say deviation minimum plus A is equal to I plus I. Okay, since they're equal under minimum deviation conditions, we can say that this is equal to this, and we add them together. This means that our delta minimum, okay, plus A is equal to I plus I gives you a 2I, right? I plus I gives you 2I. And now what do you do with this information? Let's clean this part up so that we can continue with our solution. We now say to solve for I, in this case, we simply divide both sides by 2. We divide both sides by 2. And then what do we have? The 2 cancels out, and we have that our I is equal to deviation minimum plus A all over 2. This is a major formula that we need to know. It means that the angle of incidence is actually equal to division minimum plus A. I'm going to rearrange this and put the A first because addition is commutative. It doesn't matter whether you say 2 plus 1 or 1 plus 2, you still get the same solution. So we say that the I, which is the angle of incidence, is equal to A plus deviation minimum all over 2. All right, let's write this up somewhere here. Our I, okay, is equal to the apex angle plus deviation minimum all over 2. So we call this our equation 1 for the minimum deviation condition. And what about for the other one? For the other one, we need to understand that, let me clean this up before we continue. For the other formula, we need to understand that under minimum deviation conditions, the angle of refraction is equal to the angle of incidence at the second surface, which means that under minimum deviation conditions, R is equal to R prime. So we say R, okay, under minimum deviation, okay, conditions, we have that R is equal to R prime. It's only under minimum deviation that these two angles are equal. Apart from that, they're not equal in any way. Therefore, what do we do right now? Remember that A is equal to R as we derived earlier, okay, plus R prime. Since they are now equal, okay, since R is now equal to R prime, we now say that our A is equal to R plus R, right? And what do we have left? We say that A is equal to R plus R is simply 2R. To solve for R, which is the angle of refraction, we simply divide both sides by 2, A over 2. We can now cancel the 2, and we have that our R is equal to A over 2. We can write this equation here. Our R is equal to A over 2. We call this our equation 2. What do we do with this information right now? And how do we derive that very formula that we're looking for, which is the formula for calculating the minimum deviation angle under minimum deviation conditions? How do we do that right now? So we have to now introduce Snell's law. Let's introduce Snell's law. That will help us to work on this, since we now have our I, which is the angle of incidence, and we also have our R. We know that Snell's law says that N, which is the refractive index of the material, is equal to sine, okay, of the angle of incidence all over the sine of the angle of refraction. Since this is a statement, which means that whenever we see I, we put A plus delta minimum over 2. So we're simply going to substitute everything here, okay, for I. Since this is our I, and we have our I here, we're going to replace the I in this formula with A plus delta minimum all over 2. Now let's do that very quickly. We say that N is equal to sine, we open our bracket, and what is our I equal to? Our I is equal to A plus delta minimum. So we say A plus delta minimum all over 2. Okay. Now, what about the one at the denominator? So right down here, we have our R, okay? And our R is now equal to A over 2. Therefore, we now say this is all over what's down there. We have sine Okay, we open our bracket. Our R is equal to A over 2. We now say we replace the R with A over 2. All right, so this now becomes the formula that we're looking for. It means that the refractive index is equal to sine A plus delta minimum over 2 divided by sine A over 2. This means that if you know your apex angle or the angle of prism, and you know your minimum deviation angle, divided by 2, also divided by the sine, multiplied by the apex angle divided by 2, you can get the refractive index of the material, okay, which is in this case the prism. And this is how it works. I believe you understood all this explanation. If you have any concerns, observation, or comment, please leave it in the comment section and I'll be right there waiting for you. In our next video, I'm going to show you how to apply this formula and also other important concepts in refraction of light through a triangular prism for proper comprehension. See you in the next video and bye.